Hello and welcome to this video where we will explain the benefits of using our ADQ35 PDRX digitizer for nanosecond pulse detection with coexisting strong and weak pulses. This depicts a typical use case consisting of both strong and weak pulses with a duration of 1 nanosecond or less. This example shows a unipolar signal with only positive polarity. However, this method also applies to pulses with negative polarity and/or bipolar signals. Here are some example applications where ADQ35 PDRX excels: mass spectrometry, beam diagnostics, LiDAR, and more. The first step in measuring this type of pulses is signal conditioning. This involves adjusting the signal so its amplitude is close to the digitizer's input voltage range, ensuring maximum performance. This is called being close to full scale, and the input voltage range is specified in the device's datasheet. For ADQ35 PDRX, the input voltage range is 1 volt peak to peak or 1 VPP, and depending on the amplitude of the strong pulse, the user may either need to amplify or attenuate the signal before feeding it to the digitizer. In this example, since the strong pulse has higher amplitude than the digitizer's input range, it will need to be attenuated so that it becomes close to full scale. During amplification or attenuation, it is common to leave some voltage margin in order not to saturate the digitizer in case of over or undershoot. So now we have adjusted the voltage of the strong pulse to match the input range of the digitizer. And the question becomes, what is the smallest detectable weak pulse that we can detect? For example, a 16 bits digitizer with 1 volt peak-to-peak input range can theoretically detect a signal as small as 0.015 millivolts. The digitizer's resolution determines the number of quantization levels, 2 to the power of n, and this, combined with the voltage input range, reveals the smallest detectable signal under ideal conditions. In a real-life scenario, this is unfortunately not the case, as noise and distortion will negatively affect performance. When zooming in on noise, individual noise amplitude values might be higher than the weak pulse, leading to misinterpretation. A noise histogram shows a Gaussian distribution, with most amplitude values around 0 and fewer, less probable higher values. This trade-off means that the lower the amplitude you specify, the higher the risk of mistaking noise for a weak signal. For digitizers and their analog-to-digital converters, you'll often see a specification called effective number of bits, or ENUB. ENUB represents the actual resolution under specific conditions, accounting for noise and distortion sources such as non-linearity, harmonic distortion, converter noise, crosstalk, and more. These factors reduce measurement accuracy. Here are real-life ENUB figures for 3 commercially available analog-to-digital converters, or ADCs. You will notice that while the ideal resolution is 16 bits, the ENUB is significantly lower. So, real-life performance of these 16 bits converters is similar to an ideal case with about 11 to 13 bits. It is also obvious that ADC sampling rate affects ENUB performance, and that higher rate results in lower ENUB. The underlying reason is simple to understand. It is intuitive that an ADC with higher sampling rate supports a wider band, which contains more noise, and this negatively affects ENUB. This is illustrated in the bottom figure with the analog device's ADC to the left and the Texas Instruments ADC to the right. Due to the difference in sampling rate and corresponding Nyquist zones, the ADC to the right captures much more noise, which leads to lower ENUB. Digitizers use commercially available ADCs. Shown here are two example digitizers and the ADQ35 PDRX from Teledyne SP devices. The best ENUB figures from each datasheet are used. When the ADCs are integrated in the digitizers, additional electronics, such as the analog front end of the digitizer, may introduce additional ENUB degradation, although typically not very significant. In this example, the degradation is about 0.5 bits for the digitizers relative to the utilized ADCs. However, please also recall that ENUB is reduced with increasing sampling rate, and here, the ADQ35 PDRX stands out against competition, since it offers 5 times higher sampling rate or more with preserved ENUB. It should be mentioned that it is difficult to do a fair comparison of ENUB since characterization methods may differ between manufacturers, and the ENUB figure also depends on the frequency of the input signal. But nevertheless, the ADQ35 PDRX displays remarkable performance in terms of combined sampling rate and ENUB. As previously mentioned, the ENUB reflects the digitizer's actual resolution. So let's return to our original question about detectable amplitude level for the weak pulse. It is common to specify noise level using something called root mean square, or RMS, and we denote this as RMS noise. Notice that the RMS equation is similar to the quantization step calculation we looked at earlier for ideal digitizers, and that the RMS noise levels are similar to that of ideal 11 bits digitizers. Here, it also becomes obvious that the digitizer's input range has a direct effect on the smallest detectable signal that can be distinguished from noise. The RMS value is an average, so individual noise samples can be higher. Users must set a reasonable trigger level based on their application. Some applications are more forgiving, while others need a good margin to avoid false triggers from noise. The ADQ35 PDRX has similar noise performance to other digitizers, making it equally good at capturing weak pulses. However, it stands out with a 5 gigasamples per second sampling rate, which is 5 to 20 times faster than the other two digitizers shown here. This high sampling rate allows it to capture more samples per pulse, resulting in better digital representation. This is illustrated at the bottom, where we have used an example of capturing 6 samples per pulse. One option is to use a 14 bits digitizer instead, and one example is listed here. While its sampling rate is nearly as high as the ADQ35 PDRX, its ENUB is much lower, resulting in 4 times higher RMS noise. This means it can capture short pulses, but many weak pulses would go undetected. This measurement with the ADQ35 PDRX shows a 1 nanosecond strong signal of 950 mV and a weak signal of 0.95 mV, clearly distinguishable from the noise. The amplitude ratio between the pulses is 1000 to 1, and the peak noise, marked in red, is about 0.2 mV, though this can vary slightly. So, to summarize what we have learned today, A. 16 bits digitizers are ideal for signals with coexisting strong and weak pulses. However, B. Currently available 16 bits digitizers typically limited to 1 gigasamples per second sampling rate. Whereas, C. A DQ35 PDRX offers 5 times higher sampling rate with 16 bits performance. 1. With insufficient resolution, the weak signals will be buried in noise and remain undetected as shown in the bottom left. 2. With insufficient sampling rate, short pulses will be missed and the pulse shape is typically distorted. 3. ADQ35 PDRX helps solve this challenge by offering simultaneous high resolution and high sampling rate so that short weak pulses can be unveiled. Thank you for listening and hope you enjoyed this video. If you want to learn more, then please visit our website.